Welcome to MSP lecture series on main group chemistry. In this lecture, I shall continue discussion on oxides of heavier group 14 elements. So, in my previous lecture, I was discussing about germanium oxide. Let me continue discussion on tin oxide. Tin oxide, if you consider SnO2 with tinine plus phosphate, is soluble in many acids, but it exhibits amphoteric behavior and also reacts with alkalis. Reaction occurs in strongly alkaline media to give a stannate. For example, SnO2 when treated with hydrochloric acid, it forms hexachlorostannate. Similarly, when it is treated with KOH, in aqueous medium, it gives again hydroxide, hexahydroxystannate. So, oxides of germanium, tin and lead are very similar to rutile structure. You can see here, these main group elements of germanium, tin or lead, they are essentially are octahedrally surrounded by 6 oxygen atoms, whereas oxygen is bridging or it is tri-bridging in this fashion. 6 coordinated metal and 3 coordinated oxygen is the common feature of rutile structure or rutile structure. These oxides, as I showed, are essentially amphoteric and dissolve in both acids and bases. And of course, hydrated tin and lead 2 plus ions undergo substantial hydrolysis. So, I have a question here, why is the tin 2 plus ion is more extensively hydrolyzed in aqueous solution than Pb2 plus? The answer is very simple. I read again answer I have given in the slide. Sn2 plus ion has a relatively larger charge density compared to lead 2 plus owing to its smaller ionic radius. We can compare the ionic radius of tin with lead. In case of tin 2 plus it is 93 picometer, whereas in case of lead 2 plus it is 119 picometer. So, tin 2 plus polarizes water molecule more strongly, resulting in increased loss of H plus and formation of complexes with coordinated hydroxide ion. That means here again the difference in the reactivity stems due to the fact that tin has better charge to size ratio compared to lead being smaller in size. So, that means how the size of ions can have dramatic impact on some of these properties can be clearly seen from this example. I have a question here. The lead forms the mixed oxystate oxides. That means, if we consider Pb3O4, you can see that we have 2 different type of lead ions. So, calculate the theoretical yield of lead 4 ethonate or acetate in the reaction of 1 gram of Pb3O4 with excess of pure acetic acid containing some quantity of acetic anhydride. Essentially, the role of acetic anhydride is to remove water to give back acetic acid. And note that PbO and PbO2. So, PbO plus 2 state and PbO2 plus 4 state react with acetic acid to form lead acetate and lead tetraacetate respectively. Okay. So, let me work out on this problem here. We know that, for example, composition of Pb3O4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 and Pb 3 O 4, it is essentially combination of PbO 2 O2. So, that means we have 2 lead atoms in +2 state and 1 lead atom in +4 state leads to the composition of Pb3O4. And let us look into the reaction of PbO as well as PbO2 with acetic acid. First look into the reaction of 2-PbO with 4 equivalents of acetic acid. It gives 2-PbOAc. This can also be written as OAc 2 times, and here we get 2 equivalents of water. Now, let us look into the reaction of PbO2 with 4 equivalents of acetic acid. This gives essentially lead tetraacetate. This overall reaction is Pb3O4 plus 8 CH3COOH. This is giving PbOAc 4 times plus 2-PbOAc 2 times plus 4H2O. Essentially, I have added up 1 and 2. So, that means this is the overall reaction involving Pb3O4 with acetic acid, and of course, as I mentioned, acetic anhydride, the role of acetic anhydride is essentially to abstract this water to prevent the backward reaction. So, we need to add that many acetic anhydride here. Okay. So, now calculate the molecular weight now. So, now if we the molecular weight of Pb3O4 is essentially 687.9. So, that means if we consider 1 gram, that is equivalent to 0.0014 mole. Okay. So, that means PbOAc twice is 326.0, that means should form 2 into 0.0015 mole. So, that is equal to 0.9128 gram. So, then PbOAc 4 times is molecular weight is 446, okay, should form essentially 0.0014 mole. So, this accounts for about 0.626 grams. Okay. So, this is how you can calculate the amount of lead acetate forms and lead tetraacetate formed in this reaction. Of course, we can also look into the uses of group 14 element oxides. Silica glass operator is highly insensitive to thermal shock owing to the low coefficient of thermal expansion of silica, and borosilicate glass, that is essentially also known as Pyrex, contains about 10 to 15% of B2O3 and has a lower melting point than silica glass, and soda glass contains added alkali which converts some of the SiO-Si bridges in the silica network into terminal SiO groups, reducing the melting point below that of borosilicate glass. Now, let us look into the carbides. Carbides are the numerous binary compounds of carbon with metals and metallides which are classified as follows: saline carbides or ionic carbides, which are essentially formed by group 1 and group 2 elements, and also to an extent by aluminum, and metallic carbides are essentially made up of trans elements, that is D block elements, and metalloid carbides are essentially formed by boron and silicon, and saline carbides means carbides of alkali metals and alkaline earth metals on hydrolysis essentially produce the corresponding hydrocarbons. For example, if you take simple carbide, that gives methane when it is hydrolyzed, and you can see the distribution of carbides in the periodic table. You can see this saline hydrides, saline carbides or ionic carbides are essentially formed by group 1 and group 2 elements, and to an extent aluminum, and then molecular carbon compounds are essentially formed by p block elements such as group 15, 16 and 17. They form a covalent carbon to the element bonds, and metallic ones are essentially formed by tungsten metals. You can see here in this color here, and metalloids are essentially by boron and silicon. So, this is how you can classify the carbides of the elements in the periodic table by looking into nature and the properties, chemical as well as physical properties. And saline carbides are essentially formed by, as I mentioned, high electropositive metals, and non-metal carbides are mechanically hard and are also semiconductors. Saline carbides of group 1 and 2 can also be divided into 3 subcategories. Intercalation compounds, for example, if we take alkali metals and pass their vapors into the graphite sheets around 300 to 400 degrees centigrade, we get intercalated compounds. In case of potassium, it is a KC8, that means the composition is 1 potassium atom for 8 carbon atoms, and here essentially potassium sits between 8 carbon atoms, 4 above and 4 below, giving a sort of anti-square prismatic structure for potassium. In case of calcium carbide, calcium is placed in a octahedral environment. So it goes, and also we have dicarbides having C2 minus anion, or methides having C4 minus anion. Graphite intercalation compounds are formed by group 1 metals. The dicarbides are formed by a broad range of electropositive metals that already I had discussed, talking about the chemistry of group 1 and group 2 elements. Okay. Let us look into the reactions of metal oxides with carbon. Okay. So, that also leads to the formation of carbides. For example, if you take calcium oxide and treat this one with carbon, essentially it is a reduction process, and that means that requires very high temperature of 2000 degrees centigrade. It gives calcium carbide. Of course, reaction of ethane with a metal ammonia solution gives the corresponding carbide. For example, if you take sodium in ammonia, liquid ammonia, and treat this one with acetylene, it leads to the formation of Na2C solid plus H2 comes out. Okay. Of course, as I already discussed the chemistry of electropositive carbides in their respective groups, just let me write this reaction, how they undergo hydrolysis. If it is treated with 2 equivalents of water, it forms calcium hydroxide plus acetylene comes out. So, let us look into the compounds of group 14 elements with nitrogen. Cyanide is there, very important in coordination chemistry. Cn minus forms numerous complexes with many D block metal ions. Its coordination to the active sites of enzymes such as cytochrome C oxidase accounts for its high toxicity. The toxic nature of cyanide in living beings or in human beings comes into picture because it forms a very stable complex with cytochrome C oxidase that accounts for its high toxicity. Cyanogen is a toxic, extremely flammable gas. Melting point is 245 Kelvin and boiling point is 252 Kelvin. Silicon nitride Si3N4 is used in ceramic and refractory material applications. tin 4 nitrate, that is SN3N4, was first isolated in 1999. Tin nitrate is the first nitrate spinel that is stable under ambient conditions. Cyanide is a pseudo halogen. Its chemistry resembles that of halogen atoms, and its physical and chemical properties also resembles halogens. That is the reason they are called pseudo halogens. For example, azide is also called a pseudo halogen, and it forms C2N2, HCN. For example, if you take HgCN twice and treat this one with HgCl2 at 570 Kelvin, it gives cyanogen plus Hg to Cl2. Okay. One can also prepare this one starting from copper sulfate. For example, on heating the aqueous solution, it gives C2N2 . Okay. So, cyanogen has a linear structure something like this. Okay, and of course, very similar to here. We can compare here the C triple bond N distance is, bond distance is 115 picometer, and here it is 116, marginal difference is there. And here this distance, CC bond distance is 137 picometer here. Of course, here this CH bond distance is 106.5 picometer. Okay. And so both are linear. Cyanogen burns in air with a very hot and violent flame, that is because of formation of carbon dioxide and N2. Okay. Hydrogen cyanide is extremely toxic and flammable, colorless volatile liquid, and essentially one can prepare in large amounts by high temperature catalytic partial oxidation of methane and ammonia. I will show you the method of preparation of hydrogen cyanide. Platinum or rhodium catalyst, and temperature required is very high, 1250 to 1550 Kelvin, and 2 bar pressure. Mild oxidizing agents convert cyanide to cyanogen, but with more powerful oxidants such as PbO or neutral MnO4 minus converts Cn minus to cyanate ion. Okay. So, for example, okay, so silicon nitride Si3N4 is a white chemically inert amorphous powder which can be prepared by reaction or combining silicon and nitrogen at very high temperature. For example, one can also start from tetrachlorosilane. For example, on treatment of tetrachlorosilane with ammonia, leads to the formation of amide compound, okay, which on further heating gives this compound, and which on further heating gives essentially Si3N4. Okay. Similarly, SN3N4 can also be made, okay, by starting from SNI4 plus KNH2. Okay, of course, I am not balancing the equation. One can generally prepare by treating SNI4 with potassium amide, that means potassium in liquid ammonia, at 243 Kelvin. Sulfides of group 14 elements are quite well known. Disulfides of carbon, carbon disulfide, silicon, germanium and tin show the properties that might be expected to accompany the increasingly metallic character of the elements. The monosulfides of germanium, tin and Pb all are obtained by precipitation from aqueous media. Silicon disulfide is prepared by heating silicon in sulfur vapor. The disulfides of germanium and tin are precipitated when H2S is passed into acidic solutions of germanium 4 or tin 4 compounds. Lead 4 is too powerful an oxidizing agent to coexist with S2 minus. So, and hence PbS2 is not known, similar to PbO2. Of course, PbO2 one can make, whereas in case of sulfur PbS2 is not known. Okay. When shaken with solutions of group 1 metal sulfides, carbon disulfide dissolves readily to give trithiocarbonates having composition M2CS3 that contain essentially a thiocarbonate ion. For example, barium thiocarbonate when it is treated with HCl at 273 Kelvin, it gives BaCl2 plus thiocarboxylic acid. Okay. And of course, silicon disulfide is prepared by heating sulfur in sulfur vapor with silicon. Both the structure of this and the chemistry of SiO2 show no parallels with SiO2, and SiS2 is instantly hydrolyzed. Okay. So, SiO2 is very stable towards hydrolysis, whereas SiS2 readily undergoes hydrolysis to form SiO2 plus 2H2S. Some of these sulfides of tin and germanium have cluster structures. For example, if you consider Ge4 S10 2 minus, which can be prepared starting from germanium sulfide, okay, with sulfide source, essentially cesium sulfide one can use aqueous solution in presence of cesium plus. Okay, cesium sulfide one can use aqueous solution of cesium sulfide and germanium sulfide. When they mix it together, it leads to the formation of Ge4S10 2 minus. Lead 2 sulfide occurs naturally as galena PbS, and that adopts sodium chloride lattice, and it forms a black precipitate. So, that means in the qualitative test, formation of lead sulfate from the corresponding salts is used as a identification or qualitative test for the cations. For example, if you take lead nitrate, treat this one with H2S. aqueous solution of lead nitrate when is bubbled with H2S gas, it gives PbS plus 2HNO3, and this is a black precipitate. So, this indicates presence of some of these sulfophilic metal ions. The structure of few of these higher sulfides I have shown here, SN2S64 minus here, or Ge4S10 has a cage structure, or it's similar to pyro structure SN2S76 minus, very similar to pyrosilicate. And of course, halides of group 14 elements are also quite well known. The stability of tetrahalomethanes decreases from CF4 to CI4. The rates of nucleophilic displacement increases greatly from fluorine to iodine and lie in the order like this. Okay. And of course, CF4 and CCl4 are thermodynamically unstable with respect to hydrolysis. CCl4 plus 2H2O So, carbon tetrafluoride is extremely inert and may be prepared by the reaction of silicon carbide with F2 with second product being SiF4. So, a convenient laboratory scale synthesis of CF4 involves the reaction of calcium cyanamide with fluorine. Okay, so let me stop at this stage. Continue discussion on group 14 halides in my next lecture. Until then, have a present reading of group 14 chemistry. Thank you.